So this will be the first video on the inertia tensor. I'll cover how to derive its components, its matrix representation. I'll go over some of the implications of the inertia tensor, and I'll state a property. And while it may be trivial, I'll go over it anyway. I'll begin with this classical relationship between angular momentum, a position vector, and a velocity vector. I'll then rewrite this velocity vector with angular velocity and a position vector using a cross product. And in the language of Clifford or geometric algebra, this would be an exterior product. However, that's not relevant in this video, but the next. I'll then recall an identity from vector calculus, the triple cross product, and rewrite that term into this new integrand involving two dot products. Now, this is a very trivial property. You should see that the Kronecker delta will easily eliminate all the terms except for when I equals j. And using this, I'll be able to rewrite the dot product between R and W as such into this summation. I'll then apply this identity to this term, or part of it at least, the angular velocity part. And as a consequence, I will have derived the components of the angular momentum tensor as everything is in its component form. Now, if you recall the classical relationship between angular momentum, angular velocity, and the moment of inertia, you would know that angular momentum is simply the product of these two. Now that I've factored this angular velocity term, it implies that the integral that I'm left with denotes the components of the inertia tensor. However, tensors have multiple representations. They don't necessarily have to be written in their component form, but a matrix perhaps. And I'll now go over that. Here, I'm starting yet again with the classical relationship between angular momentum, velocity, and a position vector. I've already applied this identity right here involving v, w, and r. I've also applied the triple cross product, leaving me with this. I'm also assuming a convenient mass such that I don't have to integrate over it. So I'll leave that out. I'll then break up the angular momentum term into its constituent parts, and subsequently the angular velocity, leaving with these three terms. I'll then put them all together, leaving me with the angular momentum tensor. And these are, of course, its components, but expressed as a dot product. Now, not obvious, but this term in the middle, sandwiched between the angular momentum and angular velocity, denotes the matrix elements of the inertia tensor, where where the set of three elements represents a row, with the first one in every set denoting the first column, the middle ones denoting the second column, and of course the third ones denote the third column. Now, I'm just rewriting it explicitly on its own, the matrix elements of the inertia tensor. And of course, it may not be obvious. However, if you were to actually make this into a constant mass, getting rid of the one form, you will find that this equation actually agrees with what you get down below, and these components will actually give you the matrix elements of the inertia tensor. And this at first wasn't obvious to me when I was first learning about it, which is why I covered both in this video. Now, some of the implications of the inertia tensor. Of course, you can rewrite the angular momentum tensor as such using the inertia tensor. That's obvious. Now, a more interesting implication is rewriting kinetic energy. Now, if you recall this classical relationship, kinetic energy is just a half times the moment of inertia times the angular velocity squared. However, this can be rewritten as such, 1/2 times omega transpose I omega, or omega dot I omega. That's just a very basic property from linear algebra. On a further note, I can rewrite the kinetic energy tensor as such, integrating over this one form, generalizing velocity, that was subscript, applying the relationship between it, angular velocity, and a position vector, And then, of course, if you were to square a cross product, you're left with this identity. It's another well-known identity from vector calculus, so I won't be proving it. But you can go ahead and show that by squaring omega cross r, you're left with this integrand over here. Now, I'll cover one property of the inertia tensor. It's trivial, however, I think it's good to just establish it. Now, if you were to look at its components right here, you'll find that these two are scalars. Now, in general, objects in math will not commute. Quaternions, operators, tensors, it just doesn't happen. But in the case of scalars, it does. So even if I were to interchange j and I, this will be left unchanged, and the Kronecker delta is also left unchanged if the indices don't match, it goes to 0. If they do, it goes to 1 regardless. So what I'm trying to say is that the inertia tensor is symmetric. So in other words, I sub ij is equal to I sub ji. And that pretty much covers what I wanted to go over for the inertia tensor in this video. In the following one, I'll dive into the inertia tensor in the language of Clifford and geometric algebra.